Hello guys, welcome to another video. Today we're going to work on topic 3. We'll do a couple of multiple choice questions. So let's see each one of those and their solution. So the first one, it says that an insulated tube is filled with a large number n of lead spheres, each of mass m. The tube is inverted s times, so that the spheres completely fall through an average distance L each time. The temperature of the sphere is measured before and after the inversions, and the resultant change is delta T. What is the specific heat capacity of lead? So what we have to do here is to try to solve for the specific heat capacity. We're going to use the formula for the energy transfer in our system, for the thermal energy transfer. So we want to solve this one for C. So C, it will be Q over the mass times the change in temperature. Now we need to figure out how much is this thermal energy transfer. The thermal energy transfer, it's gonna come from the change of the potential energy of these spheres falling through this distance L. So it's gonna be mgh, as we already know. And specific for this situation, we have mgl. This is the distance, the height that they cross, but they do that for s times. So I need to multiply here with s as well. So I'm going to place this equation here. So you have s mgl divided by m delta t. Of course, the masses, they cancel out. So you have sgl over delta t. And of course, here the correct answer is B. For the next one, we have a boiling water is heated in 2 kilowatts electric kettle. The initial mass of water is 0.4 kilograms. Assume the specific latent heat of vaporization of water is 2 megajoules over kilograms. What is the time taken for all the water to vaporize? So what we need to do here, we need to work with this formula for the energy transfer in the vaporization situation, like the change in phase, so we don't have any change in temperature. But what I have here, I have kilowatts, so I have power. So I need somehow to involve here power. In order to do that, I'm going to divide both sides by T. So I have power is equal to m times L over T. This is the time that I'm looking for, so I'm going to solve this equation for time. So it's mass times specific latent heat over the power. And I'm going to include the numbers here. So the time is equal, the mass is 0.4 times the specific latent heat, it's 2 megajoules, so 2 times 10 to the power of 6. And for power, I have 2 kilowatts, so 2 times 10 to the power of 3. So here, these are cancelled out, these numbers are cancelled out, you have a number of 3, so it's 0.4 times 10 to the power of 3, it's 400 seconds, of course. So the correct answer here is B. The next one, number 3. A substance changes from the solid phase to the gas phase without becoming a liquid and without a change in temperature. What is true about the internal energy of the substance and the total intermolecular potential energy of the substance when this phase change occurs? So we need to see what happens in these specific energies. You know that the potential energy, when you change phase, of course, is increasing. Okay, from a negative number, it becomes a less negative number. And this is in order to break the bonds. So of course here it's either C, either D. Now the internal energy, that it's from the kinetic energy and the potential energy of the molecules. Okay, the kinetic energy here, it stays constant because we don't have change in temperature, but the potential energy is increasing. So therefore, the internal energy will increase as well. So these are your options. Of course, the correct answer is C. The number 4, a liquid of mass m and specific heat capacity C cools. The rate of change of the temperature of the liquid is K. What is the rate at which thermal energy is transferred from the liquid? Again, here we have to work with this specific formula for the energy transfer, mc delta T. Now what we're looking for is the rate at which thermal energy is changing. So I need to divide here by time in order to take the rate, Q over T, and this is what I'm looking for. So this is mc delta T over T, of course, because I divide both sides by T. And you know that the rate of change of temperature is K. So from here you have mck. So the correct answer, of course, is D. Now we move to a couple of exercises in 3.2 topic. The first one says that you have an ideal gas is in a closed container, which changes to its volume and temperature when taken together must cause a decrease in the gas pressure. So what we have here, we have to work with the ideal gas law, that is this one. And from this one you know that the pressure is proportional to the temperature, of course when the volume is constant, and the pressure is also inversely proportional to the volume, of course when the temperature is constant. So here what you see is that in order to decrease pressure, you have to decrease temperature. So it's either B, either D. In order to decrease pressure, you have to increase volume. So it's either C, either D. Of course, it aligns with number D. The next one, it says that we have two flasks, P and Q, contain an ideal gas and are connected with a tube of negligible volume compared to that of the flasks. The volume of P is twice the volume of Q. P is held at temperature of 200 Kelvin and Q is held at a temperature of 400 Kelvin. What is the mass between of P and Q, this ratio we're looking for? So here what we have to do is to do the comparison, and of course we have ideal gas, so we're going to work again with the ideal gas law. So we have the pressure of P and the volume of P is equal with the N of P times R times T of P. The N, of course, is the amount of substance. So this is what will give me the mass. And from the other hand, for Q, I have PQ, VQ is equal to NQ times R and TQ. Now I know that the volume of P is twice of the volume of Q. So here, the volume of P, it's 2 times the volume of Q. So I'm going to take the ratio of the amount of substance of P over the amount of substance of Q. And playing with the equations here, I have the pressure of P times the volume of P divided by R times the temperature of P divided by the pressure of Q times the volume of Q divided by R times the temperature of Q. Now you know also that the pressures here in a closed container that is attached, they're gonna be the same. So from here, these are cancelled out, the R's of course are cancelled out, and I have the volume of P is 2 volume of Q, divide the temperature of P, it's 200 Kelvin, divided by volume of Q, over the temperature of Q, it's 400 Kelvin. So I'm gonna simplify here my fraction, and I have 200, and above I have 2 times 400, so it's 800 over 200, so it's 4. So your answer here is C. Number 6, it says that the temperature of a fixed mass of an ideal gas changes from 200 Celsius to 400 Celsius. What is the ratio between the kinetic energies of the gas? Now here, before you start applying the equations for the kinetic energy, you need to convert from Celsius to Kelvin. So 200 Celsius, it's 473 Kelvin. 400 Celsius, it's 673 Kelvin. And now you will use the formula of the kinetic energy. So you have the kinetic energy of the 200 degrees gas over the kinetic energy of the 400 degrees gas. And using the formulas here, you have 3 over 2 times Boltzmann's constant times the temperature of the 200 degrees gas, 3 over 2 times Boltzmann's constant and the temperature of the 400 degrees, all of those are cancelled out, and you have 473 Kelvin over 673 Kelvin. And of course here it cannot be C or D, it cannot be 0.5, this is not the half of it, so it's gonna be 0.7. You can also use the other formula here for the kinetic energy, that it's 2 over 3 times R over NA times the temperature, but it doesn't really matter. Whatever you use, they will cancel out the constant numbers, so it doesn't really matter. Be careful here, don't use the Celsius decrease because you're going to find an answer of 0.5 and this is incorrect. The number 7, it says that you have a container that it holds 20 grams of argon 40 and 40 grams of neon 20. What is the ratio of number of atoms of argon and number of atoms of neon? So here we need to find the number of atoms. In order to do that, we need to check what we have in each of our substances. Now, the atomic weight of argon is 40. Okay, you can see it from here. The mass of argon is 20 grams. So the moles in the argon, it will be the mass over the atomic weight. And this is 20 over 40, so it is 0.5 moles. I'm going to do the same for neon. The atomic weight of neon is 20. You can see it from here. The mass of neon is 40 grams. So the moles of neon, it will be 40 over 20. So this is going to be 2 moles. Now you know that 1 mole, it contains 6 times 10 to the power of 23 atoms. And this is the Avogadro's number. So in order to take the ratio between these two substances, you have to take the number of moles of argon times Avogadro's constant over the number of moles of neon times the Avogadro's constant. These are cancelled out, of course, and you have 1 over 4, so this is 0.25. And this is your correct answer, A. Number 8. Now, number 8, it says that you have a cylinder X that it has a volume V and contains 3 moles of an ideal gas. Cylinder Y has a volume V over 2 and contains 2 moles of the same gas. The gases in X and Y are at the same temperature T. The containers are joined by a valve which is opened so that the temperatures do not change. What is the change in pressure in X? So what do we have here? We have to see, in order to find the change in pressure of X, we need to know the initial and the final pressure of this gas. Now the initial pressure, based on what we have, volume V, 3 moles, it's going to be given by the ideal gas law, that it's P times V, the volume it's V, is equal with nRT. N it's 3 moles. R is constant, time temperature T. So from here you can solve for Px initial, so you have 3RT over V. Now the final pressure, it will be given by again the same ideal gas law, but you have here to include the final volume, the final amount of substance times R times the final temperature, but in this case the temperature is the same. Now we need to find the final volume and we need to find also the final amount of substance. And of course, it's going to be, for the N, it's going to be the combination of the two different gases, the addition of those moles. So you have 3 plus 2. So you have 5 mole, the final. For the volume, it's going to be the same again. It's going to be the addition of the volume on X and the volume on Y. So here you have V plus V over 2. So it's going to be 3 times V over 2, your final volume. So from here, you want to solve for Px final, and it's going to be the final amount of substance, it's 5 times R times T divided by the final volume, that it's 3V over 2. And if you simplify the fraction here, you have 10RT over 3V. The temperature again is the same. So this is what you need to do here. You need to make this abstraction. 10RT, it's the final over 3V, it's the final pressure, minus 3RT over V, it's the initial, So if you do the math here, you need to multiply both with 3. So you have 10 minus 9, 1 RT over 3 times V. And of course, it's positive, so here the correct answer is A. Now, number 17. It says, a fixed mass of an ideal gas is trapped in a cylinder of constant volume and its temperature is varied. Which graph shows the variation of the pressure of the gas with temperature in degrees Celsius? So what we need to do here is to see the relationship between the pressure and the temperature for an ideal gas, of course, from this equation, the ideal gas law. So you see that the pressure is proportional to the temperature when the volume is constant. Directly proportional, so that means that it cannot be B, it cannot be D. Now what is happening between those two? Be careful here because we have the temperature in Celsius. And we know that at the absolute zero, if you can reach this temperature, then the pressure, it would be 0 as well. Okay, but the absolute zero, it's at 0 Kelvin. Here we have 0 Celsius. So if you extend these lines here, you see that at 0 Celsius you have 0 pressure. This cannot be true. If you extend this line here, you will see that at negative temperature you will have 0 pressure. So this seems correct. The answer here, of course, is A. And the number 18, we have a sealed cylinder of length L and cross-sectional area A contains N molecules of an ideal gas at Kelvin temperature T. What is the force acting on the area of the cylinder marked A due to the gas? So we need to find here this force A. In order to do that, of course, we know that the pressure is the force over the cross-sectional area. From here I need to solve for the force, so it's the pressure times the A. But what is this pressure? The pressure is going to be given by the ideal gas law, that it's P times V is equal with Ni RT, and I need to solve here, of course, for P. That is Ni RT over V. Now from here, the volume, it can be found by multiplying the cross-sectional area times the length of the cylinder. So it's A times L. So I need to replace this one here. So I have Ni RT over A times L times A. So the A is here, they cancel out. So I have Ni RT over L. But there is nothing like this in my choices. So what do I have? I have the N molecules. So I need somehow to involve this one here. And in order to do that, you know that the small n is the molecules over Avogadro's number times R times T over L. But this relationship here, it gives you the Boltzmann constant. So from here you have N times Kb times T over L. And of course this one is the answer D. So that was all for today, guys. Quite difficult topic. Many people struggle here, but you need to practice a lot. So study hard and good luck.